In our last video, we made a quick review of state space representation of linear time invariant dynamic systems, and we went through some properties of state space models. And then we said that state space models are not unique. In fact, you can have infinitely many state space representations for a linear time invariant system, and you can switch between different state space realizations of the same system by using similarity transformations. So if you take any square invertible transformation matrix, you can multiply that with your state variable vector, and that will give you another state variable vector, and that will correspond to a different state space realization for the same system. So there are infinitely many such realizations, and out of all of those realizations, certain ones have some advantages, and we prefer to use certain realizations of LTI systems for specific purposes. So today in this video, I would like to talk about one such spatial state space representation of linear time invariant systems. And to talk about that, first, let's start with the definition of eigenvalues and eigenvectors. Take a square matrix A, and lambda is an eigenvalue of that matrix A if it satisfies this equation. Okay, so let's think about this a little bit. So we have a matrix A, which is an n by n square matrix. So we assume that it's a real matrix. So eigenvalues can be defined for complex matrices as well. But in this course, we will be dealing with real systems, which will have real system matrices. So in our case, we're interested in real matrices. So when you form the matrix lambda I minus A, this will have the following form. You will have lambda minus A1, 1 minus A1, 2 minus A2, 2, lambda minus A n. And you take the determinant of that matrix. You know, determinant of a matrix is a scalar quantity. And the determinant of this particular matrix, lambda I minus A, will in fact give you a polynomial of variable lambda, an nth order polynomial of variable lambdas. This will look something like lambda to the power n plus some coefficient c1 times lambda to the power minus n minus 1 plus. Okay, and an nth order polynomial of lambda will have n roots, and these roots can be real numbers or complex numbers. And if a root of this polynomial is a complex number, we know that its complex conjugate will also be a root of that polynomial. This is because of the fact that all of these are real numbers. Well, since A is the number of the real valued functions and by n-dimensional real valued functions, I are also real coefficients. In this case, the complex roots of this polynomial are in pairs. Complex roots of determinant lambda I minus A are in complex conjugate pairs. Okay, so the definition says that this determinant is equal to 0. Okay, so now you have a matrix. Lambda I minus A has determinant 0. So that means this matrix has some linearly dependent rows and columns. Okay, so that means you can write a linear combination of its columns to obtain the 0 column. So this is because of the fact that this is not a full rank matrix. So let's take this matrix lambda minus A, and let's call the columns of that matrix P1 through Pn. So these are column vectors. Okay. And since these columns are linearly dependent, that means there exists coefficients C1 through Cn such that when you write this combination, you can obtain the zero vector. Okay, so here's the C1 through Cn are not all zeros. Okay, so at least several of them are non-zero. Okay, so that means you can write this in this form. You can take these vectors and then multiply them with a column vector where the elements are these coefficients C1 through Cn is equal to 0. Okay, well, you call this vector of coefficients, which gives the zero vector from the columns of this lambda I minus A matrix, and you call that to be an eigenvector for that matrix. Okay, so this is this was our lambda I minus A matrix, and you call this the V the V vector. So that means lambda I minus A times V is equal to 0. Or you can write this equation in this form: A times V is equal to lambda times V. Well, at the same time, this matrix also has some linearly dependent rows. By following the same argument, you can also make a linear combination of those rows to obtain the zero vector. And the coefficients that will give you that zero vector can be combined into a vector P. So this time it will be a row vector, and the multiplication of that with the matrix lambda minus A will give you 0. So we call these special vectors V to be the right eigenvector of that matrix and P to be the left eigenvector of that matrix. So these left and right eigenvectors V and P correspond to that eigenvalue, and since an n-dimensional matrix will have n eigenvalues, there will also be n associated eigenvectors with these eigenvalues. So if these n eigenvalues are distinct, which means there are no repeated eigenvalues, then you will be sure that all of these eigenvectors will be linearly independent eigenvectors. If, however, on the other hand, if you have some repeated eigenvalues, in that case, the eigenvectors corresponding to those repeated eigenvalues can be linearly dependent or can be linearly independent. And let's make a proper definition of this linear dependence. Well, a set of vectors Vi, I is equal to 1 through m, is said to be linearly independent if this combination implies that equal to 0 implies that all the coefficients are equal to 0. And this is true both ways. So if you if you have n coefficients which are all equal to 0, then the summation will always be 0, obviously. But if you can say that this summation of n eigenvectors multiplied with n coefficients equal to 0 is possible if and only if all the coefficients are equal to 0 is true, then that means those vectors are linearly independent. Now, suppose that your matrix has n eigenvalues and n linearly independent eigenvectors. So you can write this equation n times. And these eigenvalues lambda 1 through lambda n are linearly independent vectors. Okay, so now you have again n such equations, and you can so these are all vectors, right? So the right hand sides of these equations are vectors, and so are the left hand sides. So you can take these vectors on the left and right hand sides and stack them into matrices. So you take these n vectors and form a n by n matrix on the left, and likewise you combine these n vectors on the right and put them into another n by n matrix on the right. Then on the left you can take this A matrix out of the parentheses, and the left hand side becomes A times the matrix which is formed by n eigenvectors. So I'm sorry, by the way, so these are, I made a mistake here, so these should have been v1 through vn. So the eigenvectors are shown with letter v, and lambda just represents the eigenvalues. Anyway, on the right hand side here, you can write this matrix as a multiplication of this square matrix formed by the n eigenvectors times a square matrix where a diagonal square matrix, and the diagonals are composed of the eigenvalues of that matrix. Okay, so it's just diagonal matrix with the lambdas, the eigenvalues on diagonal. So if you think about that, this matrix equation is equal to the previous equation. So in other words, you have, if you call this the matrix of eigenvectors as T, now you have this matrix equation. The matrix A times that square matrix T is equal to matrix T times an equation capital lambda, where this capital lambda is a diagonal matrix with eigenvalues of the matrix A on the diagonal. Now remember that this T is a matrix whose columns are linearly independent. That means this matrix is of full rank, and it also means that its determinant is not equal to 0. So these all equivalent to saying that T is a matrix whose inverse exists. Okay, so T inverse exists, and that means you can take this equation and multiply it from left with the inverse of T to obtain this relation. Okay, and if you look at that, it just looks like a similarity transformation, right? So if you had originally a state space system with in this form ax plus bu, and if you define a new state vector as z to be equal to t inverse times x, then this will lead to the equation that z dot is equal to lambda times z, and that's also be equal to t inverse times b times u. So in other words, you obtained a state space representation of the system where the system matrix is a diagonal matrix. And this has an important dynamic interpretation, and now let's talk about that. To understand the importance of this special form of state space model, we need to remember the solution of state space model from last week's lecture notes. So remember, if you have a state space model given in this form, the response of the system in time domain can be written as you see here, where you have the exponential matrix e to power at. So for the free response of the system, you obtain this matrix and multiply with initial condition. And if you have the forced response, then you need to take this integral. Again, you have that matrix exponential. So let's, for the moment, assume that we're considering the free response of the system. So there is no input to the system, so this integral is not needed. And the response of the system will be obtained by this function. As you see, you need to take the exponential, the exponent that calculate that exponential term, e to power a times t. Okay, so now let's come back to our system. Now imagine that you have found this diagonal form for your matrix by calculating this transformation matrix by first finding the eigenvectors. And assuming that the eigenvectors are linearly independent, then you can find this transformation matrix, and using that you can put your system into the diagonal form. Now, okay, well, you need to calculate this matrix exponential, right? But instead of a, you can use the transform system matrix lambda, and when you take the kth power of lambda, as you can see here, you will have these matrix cancellations, and in the end, the kth power of lambda will be equal to T inverse times the kth power of A times the matrix T. Okay, so that means when finding this matrix exponential, you can use this series expansion, and in the series expansion, the powers of A matrix can be replaced by the lambda matrix, and the significance of that is the power of the lambda matrix is quite simple because lambda is just a diagonal matrix. Okay, so the powers of so e to the power lambda t can be directly written as you see here. So instead of taking the exponential of the matrix, you simply take the exponent of the individual terms on the diagonal. So this simply becomes taking the exponential of these scalar eigenvalues as you see here. And you pre and post multiply that matrix with the transformation matrix T and its inverse. The matrix T was formed by the eigenvectors V1 through Vn. The inverse of that is here, this matrix. So let's call the rows of the inverse matrix W1 through Wn. Okay, so we know that T is invertible, and when you take the inverse of that matrix, we simply call the rows of that inverse matrix W1 through Wn. Okay, so this allows us to write this triple matrix multiplication in the form of a summation, as you see here. This is because of the fact that the middle matrix is a diagonal matrix. So this can be written as the summation from I equals to 1 to n. You have the scalar exponential e to the power lambda I t times vi, the corresponding eigenvector, times vi transpose, where vi transpose comes from the inverse of the transformation matrix. So this last two terms here gives an n by n matrix, and the first one is just a scalar exponential. And when you add up all these n terms, the end will be equal to this matrix exponential. By using this matrix exponential, we can find the free response of the system as follows. So let's consider the initial value problem, where the system matrix A is given, and it's started from some initial condition x0. Now, and let's assume that this system is diagonalizable, which means it has n linearly independent eigenvectors, and when you obtain the transformation matrix by finding the eigenvectors, you can obtain the diagonal form for the system. Then the response of the system will be given by this operation. But now we know that this matrix expansion can be written in the form of this summation. And when you multiply that with the initial condition, you will get a scalar term in the end. So this is a row vector. You multiply that row vector with the column vector. The result will be a scalar. Then the solution of the matrix will be given in this form, where you have a time-dependent exponential term times the eigenvector and some scalar. So this means the solution is a linear combination of system modes. So in other words, we see that the response of the system will be a superposition of the individual modes of the system. Well, this scalar time-dependent expansion term determines the nature of the response. In other words, it determines whether the response diverges or converges, or if it oscillates or not. So that the time-dependent behavior is determined by that scalar term. And Vi is a vector that determines how each state contributes to that mode. So let's say you have a divergent mode, and you will see which state variables will be diverging the eigenvector will tell you that, or you have an oscillator mode. Again, which of the state variables will be oscillating will be again determined by the eigenvector. And then that beta I is a scalar that determines the extent to which initial condition excites that mode. So how your initial condition excites the modes will be determined by scalar beta I. And let me show you an important result of this analysis. So suppose that you choose your initial value to be an eigenvector. And let's see how significant that choice will be. So let me just choose this part. Okay, so it's supposed to be on the clipboard, but it's not. So let me just go here and copy it again. Okay, so this copies it. Okay, so let's assume that you choose the initial condition to be an eigenvector. Okay, so that means your summation will be IT VI times WI transpose times VJ. Okay, so now look at this last two terms. Remember, WI is a row of the inverse of the T matrix, and Vj is a column of the T matrix itself. So we know that the inverse of the T matrix times the T matrix will be the identity matrix, which means if you multiply the ith row of the inverse of the T matrix with the ith column of the T matrix, it should be 1. And if you multiply any other row of the inverse of the T matrix with the column of the jth column of the T matrix, it will be 0. So in other words, let me come back here. So this multiplication will be equal to 1 if j is equal to I, and it will be equal to 0 for any other value of j. This means if you choose your initial condition to be any one of the eigenvectors, you can see the response of a certain mode that corresponds to that eigenvector. And let's see that on an example, because here's what I mean. So if you let the initial condition to be an eigenvector, then you insert that into this summation. And what happens is that in the summation of n terms, only one term will come out that corresponds to that mode, and every other term will drop out, and the response will be equal to this single term. And that means you will see the response of the jth eigenvalue, and the response will be observed in the states that belong to the eigenvector. So one question that comes to mind is, so if you have a complex eigenvalue, the eigenvector will be in general a complex vector as well. So you may wonder, how can you set the initial condition to be a complex vector, which you can't, obviously. So, and the next example, we will see how they can be handled. Okay, so let's take a look at this system. We're given the system matrix. It's a third order system, and it has 3 eigenvalues. There's one eigenvalue at -1, and a pair of purely imaginary eigenvalues at plus minus j. So if you draw the S-plane, one of the eigenvalues is located at here. So there's one stable mode here at -1. And the second mode is an oscillator mode, a pure oscillator mode. And the eigenvalues corresponding that are located at plus minus j. Okay. So first, let's find the eigenvectors corresponding to these eigenvalues. Well, obviously, normally we use MATLAB for finding the eigenvalues and eigenvectors, but let's just go through the steps of finding the eigenvector manually. So we have an first eigenvalue at -1. So let's call the eigenvector corresponding to that as x, y, z. We don't know what these x, y, z are, and that's what we're trying to figure out. Then we insert that eigenvector into the equation. A times v1 is equal to lambda 1 times v1. So this is that equation here. So basically we get three equations in terms of these three unknowns, x, y, and z. So the eigenvector solution is not unique. The eigenvector just shows the direction, and any vector along that direction will be an eigenvector. So that means we don't get a unique solution, but we only can find y and z in terms of x, and that will give us this solution. So this is the direction that shows the direction of the eigenvector, and any scalar value of x here can be inserted, and the result will be a valid eigenvector for this mode. So we can do the same thing for the remaining eigenvalues as well. The second eigenvalue is, let's choose this to be the second one at plus j, and the third one is the conjugate of that. So once you find the second eigenvector, there's no need to find the third eigenvector, because the third eigenvalue is the complex conjugate of the second eigenvalue, which means the third eigenvector will be the complex conjugate of the second eigenvector. So since this is a complex eigenvalue, this time we choose eigenvector to be a complex vector. So instead of x, y, z here, I'm assuming complex numbers may be present here. So we have three unknowns basically. But the same equation will allow us to figure out the eigenvector direction. And these are our equations. And these equations allow us to write the second term in terms of the first term, and the third term in the eigenvector in terms of the second term. So basically, so once you pick a value for the first element of the eigenvector, you have a unique solution for the eigenvector. So if you let the first element to be the 1 without any imaginary part, the eigenvector corresponds to turns out to be this value. So it has negative j in the middle, positive 1 in the first location, and minus 1 in the last row. So as I just explained above, the third eigenvector will be the complex conjugate of that, which is this eigenvector. So now we have the three eigenvectors found for this system. So if you put these three eigenvectors to form the transformation matrix, the transformation matrix will become a complex matrix. So let me just put that here. So you put V1, V2, and V3 here. And if you put in the values we found, it's 1, minus 1, and 1 here. It's 1, minus j, and minus 1 here, and 1, j, and minus 1 here. Okay, so this is a transformation matrix. As you see, it contains complex terms. And if you insert this into this expression, let me just make sure that I write it correctly. It's going to be t inverse times a times t, and it will be a diagonal form, but unfortunately it will contain these complex terms on the diagonal. Okay, so if you try to proceed with this form, then in order to be able to excite the mode, you will have to choose it. For instance, to excite this oscillator mode, you will need to insert the start system from an initial condition that contains that imaginary term, obviously, which is not possible in real life. What we can do is, we can, instead of putting the system into this diagonal form, we can put it in a black diagonal form, where these complex terms or imaginary terms will be replaced by a 2x2 block with real elements, and the eigenvalues for that block will be equal to these complex eigenvalues. And the way to do that is explained here in the lecture notes. So instead of choosing transformation matrix as the three eigenvectors, which we know that the third eigenvector is the complex conjugate of the second eigenvector, what you can do is you use the first eigenvector, which is already real. Then for the second and third ones, you use the real and imaginary parts of the second eigenvector. So this will give you this transformation matrix, which is all real numbers, as you see. And the inverse of that can be found as this one. So I found this inverse using MATLAB here. And in the end, if you use these matrices in the similarity transformation, the resulting matrix will be in this black diagonal form. So this is in black diagonal form, and the first term is already a real eigenvalue. So this was our first eigenvalue, and the second black in the diagonal term in the black diagonal is a black matrix, and this 2 by 2 matrix has eigenvalues plus minus j. So if you want to excite the real stable mode here, what you have to do is you just choose your initial condition to be the eigenvector corresponding to that. So if you choose x0 to be this vector and simulate the system, this is what you get. If you simulate the system starting from these initial conditions, obviously you can scale it with anything you want. And this is the response. This is the time history of all three state variables. And as you can see, they start from the corresponding initial values. The first and third state variables start from +1, and they are this black and red dashed lines. They start from here, and the other second state variable starts from -1, and they converge to 0. And they do that with a time constant of 1 second. So you can just verify that this corresponds to that mode. So you have e to the power minus t times, well, this is basically the response for these, for the first and the third ones, and for the second one, there's a negative sign in front of it. As you see, while we know that the system has a pair of purely imaginary poles, we don't see any sign of oscillations at all. And this shows that if you choose the initial conditions carefully, that oscillator mode will not be excited at all. And all three state variables, this is important, all three state variables represent a behavior that obeys the dynamics of the first mode. And if you want to excite the oscillator mode, what you have to do is you need to release the system from an initial condition that corresponds to this initial condition, or this, or any linear combination of these two. So if you choose the initial condition to be in the space spanned by these two vectors, then this time the first mode will not be excited and only the second mode will be visible. And let me also show you the results of that one as well. So I just choose the initial condition to be this vector, and the results are here. Well, this time we see that all three state variables oscillate at the same frequency, and it is important to note here that all three state variables oscillate. Whereas in the first case we tried, all these three state variables showed a stable converging response, and this time they just oscillate, and these are pure oscillations. Well, it may be difficult to see here, but all these change according to this sine omega t, and there may be some phase shifting, but what's important is that this is a pure sine wave. There's no sign of a decaying or a stable component here. So in other words, we don't have something like this. Okay, so there's no such decaying component here. So they start from these initial conditions. These were our initial conditions, 1, 0, and -1. And they start out as pure sine wave oscillations, and they continue forever. Okay, so this is now we're seeing that the oscillator mode of the system is excited, and this is by just choosing the initial conditions accordingly. Okay, so if you choose the initial condition to be composed of these two spaces, so in other words, if your initial condition contains a component along this direction and a component along these directions, then both of the modes will be excited at the same time. And this is the last case in our example. Okay, so this is how I choose my initial condition, the first eigenvector, and -2 times the second vector in our transformation matrix. This corresponds to 1, 1, and 1. The response is shown here. Well, this time we have, as you see here, all the state variable start from the same initial condition of 1. And eventually, they converge to these purely oscillating signals, which is expected because we have purely oscillating mode. But what's different here is if you look at the first part, the first few seconds until the stable mode dies out, we see the effect of that mode. So in other words, if you compare this with the result of the second case, in the second case, all the three state variables started as pure sine waves and they continued like that. But if you look at here, you can see that the oscillations contain the effect of the stable mode, and within like 3 or 4 seconds the effect of this the stable mode dies out, and all the three state variables continue as pure sine waves. But this first part where the oscillations are not pure sine waves is an indication that the stable mode has been excited here as well, in addition to the oscillatory mode. And if you write the analytical expressions for the response for this case, this is what you will get. So let me just change the color to blue. So for that case, these state variables change like this. So there's a component here, ci1 times e to the power minus t plus ci2 times cosine t plus ci3 times sine t. And so this part disappears after a few seconds, and then what's left is these purely oscillating parts. Okay, so the difference between the second case and the third case is that in the second case we didn't have this part at all, and it was just pure sine waves from the very beginning. Okay, so I think this is a nice example, and this nice example shows that through similarity transformations, you can transform your system into a mode where you can see the modes separately. And by utilizing this special form, it is possible to find the necessary initial conditions which will excite you that mode. And also you also see how each mode affects the state variables. For example, if you consider an airplane, conventional airplanes have some well-known longitudinal modes like the phygoid mode and short period mode. And if you have a model for that, you can, in addition to what the characteristics, dynamics of these modes in terms of natural frequency and damping ratio, you can also see which variables contribute to that mode and which variables are excited more than the other in a particular mode. And if you want to observe these modes on an aircraft, you can use this analysis to figure out how you should excite that mode by bringing your airplane to a certain initial condition and then release the controls and see how it behaves afterwards. So let's wrap up this video here, and in the next video we will continue with a review of some basic concepts from linear algebra and important concepts from control systems like controllability and stabilizability. Okay, so I will talk to you in the next video.